Yeah. Yeah. Okay. Yeah. It's a little bit. Yeah. You just here. Yeah. So that's what you do. Yeah. Yeah. There's our president. So we're going to go through that whole paper on Thursday. And these out because other bookkeeping things, site homework number 2 is due on Friday. So just a reminder, office hours, if you need help, are today from 3 to 5 and Wednesday from 4 to 5. In my office to help with any questions you have. And then also homework 1 is finally graded. If you haven't seen that yet, it's on Carmen. You can check out your grade, see comments that I left in case there were any. Etc. The solution has been up for a while now, a few weeks. So you can check your answer against the solution. I had a few mistakes in my solution, so I would not have gotten 100% like some people in the class did. So you can see this updated solution added to it as well. Okay. All right, so today we're going to get somewhat far, not completely into this, into heat transfer and directed energy deposition and material extrusion. So I lump these two together, not because they're physically similar, they're actually very different from each other in terms of the physics of them, but because they're both going to be fairly brief topics. It's not as complex. Well, DED, I would say, is just as complex as powder bed fusion, maybe a little bit more so, but it's also very similar to powder bed fusion. So I'm going to go through some of the kind of systems level description of DED. And if you look through the literature and look at how people model DED, it's almost identical to the way people model powder bed fusion. Very, very similar the way they do this. There's one small difference for a certain type of DED, and then we're going to start to get into material extrusion. I think by the end of today, we'll just be able to get into kind of introduction to what material extrusion is and what current research process is. I think everyone's probably very aware of MakerBot. The most visible case of additive manufacturing, and then material extrusion. Those are in every classroom in every high school, it seems like, anymore, or university. But there are also a lot of emerging material extrusion processes that are going to be important for biomaterials, actually. So getting started with this, there's the basic outline. Pretty brief. Most of this module is actually going to be what is both of these, and we'll get into some examples for heat transfer. So directed energy deposition, open homework 1, you got to see some examples of what falls into this classification. But then within directed energy deposition, there are 3 basic types that are what I would call subcategories of this. So just to note, though, sorry, skip this. Additive manufacturing process in which focused thermal energy is used to fuse material when melting as they're being deposited. This is what makes this different than powder bed fusion, that the material is not in a bed, it's being essentially pushed or shot at the location of where it's being melted. The main difference. So this has been primarily used for metals. You don't really see it for polymers, even though you could. There are polymer welding systems, etc. Mostly for metals. So if you go to the literature, almost every single one of the papers you'll see is for metals, except there are a few that are kind of interesting. People use this for glass, actually. So I'll show some examples of this. This is actually maybe tough to see because glass is transparent, but this is like a glass spring. There's air in between here. So you can do some interesting things with making things out of glass, which glass has interesting properties, right? You can use different applications. So the 3 major subclasses of DED would be blown powder. We'll get into some videos, examples of this, but basically you have a laser beam. that this looks like a lot like powder diffusion. You have a laser beam on the surface, but instead of the powder being in a bed that you're adding to, you are actually shooting powder so that the powder and the laser all end up hitting the exact same point. That'd be one type of process. In your homework one, you will see this in terms of the Optimex system. Laser or E-beam wire fed. So these next two are wire fed ones. One is which would be wires just fed in, and then externally there is some sort of energy source. So either it be an electron beam or a laser, then meeting where the wire meets the part. You also have the energy source meeting the wire at the location, creating a melt pool, fusing in that location. And then slightly different to this would be external energy source. This is the energy source in that the energy is actually running through the wire in the case of arc welding. You're putting a high current through that, that's creating an arc or a plasma at the interface between the wire and the part, where this part has to be electrically grounded. So you're creating a circuit with the system. And so you have that welding at this location. This is basically taking an arc welder, which is decades old, and putting it on a robotic system to create an additive manufacturing. These are schematics from that survey paper. I think the schematics are very good at overview, but they don't really show all that well what's going on. Sorry, this is probably too small to read. But this is showing some of the components here a little bit better. These are powdered jets. Here, this is just showing a cross section. A lot of these systems will have 4 or even more of these powdered jets. Some of them will have like a complete sheet where it's all coming from a ring. But then you have a laser in the very center. Right? So these are all along the same spot. This is showing wire-fed laser in this case. This is showing the interface of the wire coming through, being fed in, and then you have a laser hitting this, and then the melt pool following behind it. This is then just a schematic of arc welding in terms of what's going on. We have, in this case, welding wire. Around this, you have that inert gas to make sure that the surface doesn't oxidize. And then you have molten metal pool here, coming from the fact that you have very high energy power supply, causing the material to arc and then melt. That's the basic thing. Okay. So I showed this table. We went through powder bed fusion, and I created another one. We kind of look at the differences and also talk about some naming conventions, important companies, etc. So with the blown powder systems, the most commonly used term is lens, laser engineered net shaping. Okay. And if you look at the ASTM names and you look at the names come up with companies, the ASTM names are much, much better, in my opinion. Laser engineered net shaping. That could be like anything, right? That could be laser cutting, in my opinion. So this is what Optimex calls their system. It's a trademark name. So if you ever see lens, they're actually referring to blown powder directed energy. The environment, I think, is interesting to think about. So these are either air environments or with shielding. So again, just like the powder bed fusion systems, if you just were to melt metal and air, you're going to get incredible amounts of oxidation on the surface, which is a negative material property. And so either you have an argon environment, just like powder bed fusion, or you have air with some sort of shielding gas. So you'd actually convey particles in a air fluid. I guess air is the wrong word, but through a gas that's argon, and therefore in the immediate vicinity of where things are melting, it's completely covered in some sort of inert gas, like argon or nitrogen. Usually room temperature. If you look at the energy sources here, um, all these, you'll notice that they're actually at a different scale, a few orders of magnitude larger than we see with the powder bed fusion. So quite a bit higher. So in powder bed fusion systems, you maybe the really high power systems will go up to 500, maybe 1,000 watts. And if you look at some of these, they have some lower wattage ones, but then this also goes all the way up to say 42 kilowatts. A lot of that. So it's a higher energy level. And the reason why it's a higher energy level is because everything you're doing here is a larger melt pool diameter. Okay, so the wire that's being fed in is fairly large in diameter. It's tough to make wire that's mechanically sound, that's considerably small. You can't make a 30 micron wire and have it be able to be fed the system. So you have fairly large wires, and the powder you use is about the same size, it's about the same feedstock, but this is fairly used for more near net shaping, not actually making the final part, but getting something close to it. So the energy levels, because you have to melt such a large amount of material, this is about 10 times or more, yeah, right, about 10 times larger than the type of features you get with powder bed fusion. And so it makes sense that the energy source has to be around 10 times as large as well if you want to melt that amount of material. Build sizes, again, these are considerably larger usually, and I'll show some examples of the type of tools. These are large enough that you can walk in a lot of them. They're quite large. And they can also deposit quite a bit of material pretty fast. So on the order of, say, 5 kilograms per hour, which is a lot. Another differentiating factor between these and powder bed fusion is that essentially support structures are, for all intents and purposes, really not possible. And so it's not that they're not possible per se, but it's not really needed. And I think you'll see in a little bit is that the purpose of a lot of these processes is to get the part into the approximate shape, and then you do finish machining anyhow. Okay, so if you're already going to put this in a CNC and machine a finished surface, why go through the extra, basically, intricacy of making this kind of sacrificial support material because you're just going to machine it away anyhow. So for the most part, support structures really aren't used. It's actually just building a larger structure than necessary than machining away what you actually is something I do. Okay, so I kind of talked about this in tandem, but going back to wire fed and laser and e-beam, some ones you'll see is Siaki is, I don't even know how to pronounce that. Siaki is a big player in this electron beam additive manufacturing. And then wire fed arc welding. Basically, any company that does arc welding or used to made arc welders, which are a very mature, very established industry, they're now just putting them on robots, turning them into additive manufacturing. So you have really well-established companies like Lincoln Electric, which has been making arc welders, all types of welders for decades, are now getting into the game. Norsk Titanium is a company from Norway that's been got a lot of press for some of the things they're doing, et cetera. But these are basically modified welders. Yes. Yeah, we'll get to that. It's essentially the same powder. Yeah, not much of a difference. Any other questions on this kind of table rough landscape? All right, so when I said before that some of these systems are large enough to walk into, here's an example of Siaki's system. This is an electron beam system, and so here's a computer, and then here is this machine. So they're gigantic. They're really, really large, and this is done under vacuum. So I don't know what this system costs because not too many people are buying these because they're probably so expensive. But anytime you have a vacuum chamber of this size, you're talking about a lot of money. So I don't know what I should research that. But this is an entire vacuum chamber for this. So these are huge, huge industrial tools. This is the wire-fed electron beam system. This is a considerably smaller system. This is the Optimex Lens 500 system. So this would be ports for glove. They turn this into a glove box. You would stick your hands in here. So you can see that this is considerably smaller than this system here. But this is showing what's at the nozzle here. So these would be the 4 jets right here. So looking at, if you were to go into the machine and kind of look up at what's above you, you would see this view, and then through the center here is where the laser comes and intersects with this is particle image velocimetry, which is a way in which people visualize fluid flows of these jets. So you can see these. This is the side view is probably the best you can see. But you have these 4 jets coming down, and then you have where it's all meeting and then flying everywhere. You're basically creating this stream of powder that's hitting this. So we won't talk about this yet, but you do have some powder waste, just like you have powder waste with powder diffusion. As you can imagine, not every single particle is going to get fused into the melting. Some is just going to go elsewhere. A considerably high percentage will actually be trapped in the melting. In terms of materials, the powdered metal materials are essentially the same with powder diffusion. So everything that we talked about with powder diffusion, in terms of the powdered metals, is the same, not so much of a difference there. And so you're still talking about stainless steel materials, regular carbon steels, titaniums, Inconels, all those materials are usable. With the wire-fed systems, you're using wire. And this is a considerable advantage of these systems because wire is pretty cheap, metal wires, apparently. So powdered metals are pretty expensive. Powdered wires are very, very cheap. So here's an example of stainless steel wire, $44 for 5 milligrams, which is not all that expensive. A little bit more expensive than milk, I guess, but it's not much more expensive than milk, right? So it's pretty cheap. And so then people have done a lot of price comparisons. So this is just a real recent paper looking at kind of the economics of some of these processes. They call the process wire. I forget what actually the first name was. Wire something additive manufacturing. But basically, everyone has their own name. But this is wire-fed GDAM. This would be powder bed fusion E-beam. Let's play comparison. This would be PVF laser for direct metal laser sintering, and they're doing price comparisons between these showing around a 45% or 79% reduction in cost by doing some sort of wire-fed system. This is including the fact that you have to machine it if you want to get the tolerances that you get with these other processes. And then they also compare this against just conventional CNC milling, that if you were to take a very, very large block of material and mill out that part, how much would it cost to do that? So again, a price savings for some of these examples. So that's one of the reasons people are so invested and interested in these processes. I think you'll see this in a second. The next slide, yes, exactly. What this allows you to do is do what's called near net shape fabrication. This is why it's potentially impactful, and I think you'll start to see this even more so in the future. So this is Norse Titanium. I introduced this company on Module 1, probably first or second day of class. This is using titanium wire and then doing plasma or just arc welding of these parts. And so this is for aerospace parts. So the traditional way in which a lot of these parts will be made is they'd either be forged, or you'd have a very large block of titanium. Titanium is pretty expensive, and then they would mill out this part. And so what this allows you to do is instead of having an entire billet of titanium mill out, you just build approximately that shape, and then you mill out to get the final finished surface. So this is a company, they're based in Norway, but they just built a, I don't know how many millions of dollar facility in New York State, upstate New York. Definitely a concern. If you talk to Norsk Titanium, they tell you that they're meeting forged part quality. I can't say I've independently looked at their plans to verify that, but yeah, they're hoping it. The only reason why I know a little bit about them is because I used to be a faculty member at Notre Dame, and then the CEO of this company is a Notre Dame alum, and he was at Notre Dame trying to get money. He was touting everything about it, and their basic plans is they want to be bought out by Boeing. That's what they know. So they set up shop in New York State, have a U.S. presence. I think they're attempting to be bought out for a lot of money. So they're specifically targeting the aerospace industry. So I guess I hope they're meeting the quality standards that aerospace industry needs, but I can't say. Okay. So in terms of anatomy of a part, so with powder bed fusion, you don't have the same surface quality of a milled face that you would have with CNC milling. You have some sort of roughness. I think you probably saw that in the parts I passed around. You can see that the surface quality is considerably worse with these processes. This is pretty bad. You would not expect to buy a product and see a surface quality like this, right? So it's not, none of these processes are actually intended to be the final part. They're intended to be that near net shape of the structure. So that's why basically support structures are not existent, because you're going to be putting this in a mill anyhow to get rid of all that excess material, etc. It does limit you in terms of one of the advantages of powder bed fusion is that you can have internal structures that would never be able to be reached by a mill. You really can't have these. So some companies are finding ways around that. I'll show you the Optimex system that has ways around that. But in general, you're going to have very rough surfaces. The other thing that's interesting about this is you can build on existing parts. So here's an example. This is Miller, which is a welding company. Don't know why the video is choppy. This is basically showing robotic arc welding. Very choppy video. This is more of a thermal camera view. You can't really see anything else except for the really hot melt pool. And then this is showing basically using coordination of robots and the welder to build. What they're building is these turbine blades or propeller blade on this cylindrical structure. High-speed imaging. This is pretty cool looking. We'll go back to the printing on that cylindrical surface. Oh, no. And line, maybe. There you go. This is basically, the video is not choppy anymore for some reason. So you can see it, basically coordination of this rotating member and the arm of this robotic system, they're building on existing parts. So one of the things that people think is important for is repair of structures. So really expensive pieces of equipment, you have something break, having the ability to repair that structure by basically building up metal where you had something to break. So cleaning out the surface, building up metal, remachining, the ability to either prevent replacement, etc. So this is an example of this propeller. very, very rough, and then in a second you'll see it machined to be of finished quality. So that's after finished machining. Again, this is the idea of the poor service quality. Here's the lens system from Optimec showing their solution for some of the service quality issues that they are now building hybrid systems. The idea is you have blown powder BED and also machine tools all built into one system. So at every layer, they're basically adding material and then they're subtracting away to get the finished surface as they build. I don't know what that says. So here's the Optimec system. So enclosed environments. This is, you can see then the addition of material here. This is the BED head, adding material. And then here is in the same system, without ever removing the part, you have then a mill. And so what this allows you to do is if you have some sort of internal structure that you want to be finished machine, you can do this because you are at certain layers that internal structures will be open. It doesn't really help if you have something that's on the top surface, but it does allow you to get some better quality. So here's a part. In a second. Not the best image, but you can see that it comes out with a better surface finish. So there's ways in which people are integrating multiple systems into one as kind of a very versatile manufacturing center. You look at CNC manufacturing centers used to be all about removing materials. Now you can think of how you can add materials in the same type of setup. Other thing you can do is you can start to merge dissimilar materials. So here are two different materials that if you have the right basically material selection, you can have merger of the two different materials. So here's a one weld metal on the left-hand side, and another one metal on the right-hand side. Here showing a weld bead merging two. Hard to talk about composite materials. Not really doable with powder bed fusion because you're scraping this powder across the surface and you have a lot of mixing when you do that with the recoater blade. And you would also never ever be able to separate those materials afterwards if you ever wanted to reuse that material. It's impossible unless you had some sort of magnetic difference or something, or you can separate them. It'd be very difficult. But you can actually pretty easily get composite materials. So here's the interface between the two of them, which makes for some interesting things. I haven't seen too much about this yet, but I think there could be some definite opportunities there for things to do. Energy source path. So with powder bed fusion, it was actually fairly simple in that you have this kind of Cartesian coordinate system, X, Y, Z, and that stays essentially constant the entire time, right, where X, Y, and Z are. With these processes, it gets a little bit more fuzzy. So here's a video I showed in the module 1 as well, just a repeat, but in a new context, talking about how the definition of a z-axis is kind of continually changing. So you'll see in a second that this is a rotational system. It also has the ability to rotate in other directions. This is obviously sped up, right? This is going faster than real time. All right. A little bit is going to rotate. There we go. Okay, so the definition of what we call the z-axis is a little bit more complicated to understand. And so that makes for some complicating factors. Also some really good opportunities, because where we're limited in terms of support structure, design, et cetera, upon Fusion, you can look at how you can design your process such that parts are supported more easily. There's also some important things to consider in terms of how weld pools are fed. So this is examples of front feeding, back feeding, side feeding. These all create small differences in terms of, this is with the wire fed systems, small differences in terms of how this performs. And then video. This is with glass manufacturing. And so with this, they had really stringent requirements. It always has to be, I guess that would be front feeding as it is deposited. So you have to rotate the table such that whatever direction you're going, you're always front feeding the weld pool. So they're making this pretty intricate structure. And so you can see that now you have to have all this robotic coordination to pull this off. It's a lot of more on the robotic side, less so on the material science side to get this to happen. So you have some pretty complex robotic systems to perform this task. Does everyone see that? What's going on here? Is it clear? So I'll rewind that just to. Okay, so just so it's clear to everyone. Okay, so this is a wire. This is a glass wire that's being fed over here, and then they have there's a laser coming down in this direction to open this, and so they always want to keep it in the front feeding scenario where the weld pool is behind where they're going, and so then they have to rotate this table and build a proper corner to get this to work properly. So pretty complex robotics problem to pull this off. Okay, so how do you do this? This is going to be very brief. In terms of, I just want to give you kind of a flavor of what's involved with these robotics problems. If you really want to understand the robotics problems that are associated with, say, you're going to have to investigate far outside this class. It's a pretty involved topic. This is, if you want to really learn about this, your best bet is to take MECAN 7752. The class I taught last year, and Srinivasan and the other departments right now this semester, but it'll be offered again next year again. So this is a very formal way of computing all, basically the motions of the different stages. Also, there's some really good books that will give you more information on how to do this. I'd recommend these three right here. But the main idea in terms of discussing the complexity here, just so you have a general taste of why this is a complex problem, is in powder bed fusion, you have what's called the zero frame, which is basically your base. Right? So this is some sort of landmark that's fixed to the ground, bolted to the ground. That you specify this is my base, and then where your laser is, you can define as some sort of basically translation from that position, right? X, Y, Z. Right? So we say the laser is at position 1, 1, 2, etc. Right? And so this is given by what's called just a translation operator, which is basically translates from the zero frame to the tool frame, which is given here. The frame is just basically a coordinate system. So a coordinate system has a position and an orientation associated. So powder bed fusion, you're looking at purely Cartesian space, and so you just have a translation of your tool frame from your base, right? The laser moves relative to sort of fixed surface. So that's pretty simple, right? With some of these DED tools, you're getting into more complex coordinate transformations where you have not only a translation given by the same exact translation operator, but you also have rotations as well of the different frames. So if this was your zero frame, something fixed to the ground, your tool frame can be both translated and rotated with respect to that and how we define that rotation. So those of you who the undergraduate kinetics class, you may have only seen two-dimensional rotation matrices. These are three-dimensional rotation matrices. Rotation matrices they have to know about. The other complicating factor is that robotic systems are there's not a unique mapping between the axis of the robotic system and actual end effector or tool types. So here's like a really simple example of this is what's called the Puma robot, which is like the classical robot example. This tool frame, which is basically where this end effector is exactly in the same position and orientation in every single example here. But you can have all these different configurations of your robot that give you that exact position and orientation. So you have, there's not just one solution in terms of how you determine how do you move all your axes of your robot to get this location that causes a bunch of different issues with singularities, etc. I guess if you're really interested in this, I guess I recommend you take this class to understand how to do this. You can't possibly do it. When I teach this class, it takes me about 8 weeks to get to solving all the different configurations of this. So we don't have time. Any questions on this? Yeah. I'm going to very briefly go through some of the physics of this because based on all my reading the literature in DED, it's essentially the same physics as powder bed fusion in terms of heat transfer, with one exception. I'll talk about that a little bit. It's not too big of a distinction, but basically what you first have is you have some sort of energy transfer, and it's transferred to the blown powder or wire, and it's spatially distributed as long. Right? So this is almost a verbatim copy of the slide from powder bed fusion. This is the case in both wire-fed models and blown powder models. I'm just giving two citations here. There are many examples of this. Everyone has their own flavor in terms of how they define these variables, but this is essentially how we define how laser or arc or e-beam energy is transferred into the system. This is Gaussian, Gaussian model for the distribution of it, just like powder bed fusion. The second part of this, in terms of then how is heat, and once it's incident on the part, how is it transferred to the rest of the boundaries? You don't necessarily have a lot of powder around anymore. You have very little powder in case of the blown powder systems. And essentially, any powder that doesn't get melted just blows away and goes somewhere else. You have a little bit. But you have fused metal, you have any support structures that exist in the build chamber, and this is all done via conduction, convection, radiation, and evaporation. Right? If you look at these models, they're almost exactly the same as the powder bed fusion system. And that's because we assume that the conduction into the powder in powder bed fusion is essentially zero, and here you don't have any powder. Physics almost end up being exactly the same. So a lot of things that we learned from powder bed fusion are going to apply to directed energy deposition. The main difference is with wire-fed arc welding systems, and this is because you have an electric current running through the weld pool. And so just we have Marangoni convection and high bit fusion and all of these processes, but also you also have another extra force that causes convection in the melt pool where you have these wire fed systems. It's called coming from Lorentz force. This is something you probably saw if you go back to your freshman or sophomore year physics classes or some sort of electrical machines course. Um, you understand that the charges in a medium can be forced by both electric field or magnetic field. So in this case, you have both that are happening here with these types of processes. You have a current that flows into the part. So here's your part. Here is then your arc coming down. And cold metal has a higher conductivity than hot metal. So you get your current actually flows towards the cold metal direction. And that creates this Lorentz force, which creates these circulating pools where you have these forces that go in this direction. Actually, opposite of your typical Marangoni convection. So you have now these competing forces that are important for the effective heat. I'm not going to get too much more detail on that. I just want to make sure everyone's aware that this is a factor. Okay. With that, I'm actually going to switch to material extrusion. That was a very quick overview of DAD in terms of the physics of heat transfer. And the reason why it's so brief is because it's so similar. So just kind of one of the points that some of the similarities, but one difference. I think I'll take a 5-minute break here. This is a good transition point, and then we'll reconvene in 10:10 or 9:10. So who has ever printed something with a MakerBot or similar technology before? Only two people? What? Maybe. What did you do with maybe? What bridges in it? Was printed? Yeah. Probably a MakerBot or similar technology, right? So what often was called fused deposition modeling, right? These ASTM standards called material extrusion. So material extrusion is a little more broad than the MakerBot type ones, in that those are melt processed material extrusion systems. Are also room temperature ones that I think are important to know about too. And we'll go through some. When we get the fluid mechanics part, we'll go through some of this in more detail. Since it's at room temperature and there's nothing thermal about it, I'll just introduce this in terms of the technology, but not really much to describe here in terms of heat transfer. You definitely have heat transfer in the melt process. Have you ever printed something with a MakerBot? No, never? 2 out of 6? Wow, I thought it'd be higher than that. Okay. 2.5 out of 6? No, okay. All right. Well, if you include me, that would be 3 out of 7. Printed something with a MakerBot like tool. So I think everyone has seen one running before, right? Is that the case? Yeah. Or have you seen like a MakerBot or material extrusion system running before? Okay. Yeah, they do. Yeah. We have I don't know how many in the department, quite a few. So basic idea is material is selectively dispensed through a nozzle or orifice. And you basically just coordinate the extrusion of this material with the positioning of it. Pretty simple idea, and really, it really has only come to being and because of robotics have gotten so cheap now that it's possible. Where it was before, but it's a pretty simple idea. So we'll talk about some of the leaders in this, but this was developed out of Minnesota by a guy named Scott Crump, the guy who started Stratasys, that took off, and you see it everywhere in terms of MakerBots, etc. The main idea is you have the feedstock material is in filament form. This is usually a polymer, not always a polymer, but almost always a polymer. Filament form, we have these little feeding rollers that just grip onto this polymer filament, and it pushes it into this heating element, which turns the solid filament into a molten filament. It comes out the nozzle, and so it's basically going solid, liquid here. And then when it extrudes out the nozzle, then the heat source around it goes away, and that's has ambient temperature on it, so it solidifies again. So you're making things by a phase transformation, just like powder diffusion. So the other methods, you're basically going from solid, liquid, solid, right? So this is the main idea. This is, of course, on an XYZ stage, distributed by these arrows here. There are many different configurations. You have ones in which the extrusion system is doing all the moving. You have ones in which the substrate's moving. It does not matter. The basic physics is the same idea. But you end up getting these, what are called filaments or rods. Some people call them more rods that are being laid down apart to make parts in a row by row or rod by rod or filament by filament, layer by layer fashion. There are room temperature methods as well. Something that I've looked at a lot, where you are using, where it's purely in a liquid phase. I'll go through some examples of this. But what you're doing is you're using materials that have certain interesting viscoelastic properties that when they're not under shear stress, they behave like a solid, and that they have a really thick consistency. And then when they are under shear stress, which is when they're being extruded out of nozzle, they act more like a liquid. So then you get the same idea of going from solid-like to liquid to solid-like, just as you would get with these melt processes. materials, but purely in the liquid phase. It's always on liquid. It just depends on what the viscosity, how it behaves in that certain shear regime. Okay. So we'll talk a little bit more about this when we get into the fluid mechanics portion of the class. That's the main idea here. So you can get the same ability to build parts if you have materials that have kind of really well tuned viscoelastic properties to them. Okay. So again, looking at this chart here and some of the important characteristics, the most commonly used term for the melt process methods is fused deposition modeling. You'll see this everywhere. The most commonly used one. Fused filament fabrication is another one. You see also a subclass of this is just big area additive manufacturing. This is the one where they're trying to print houses and cars and what have you, really large structures using this, because these methods are pretty cheap. Polymers are pretty cheap. The tool you can make it pretty big, pretty cheap as well. Environments, almost always air. You don't have to worry about oxidation with polymers. Environmental temperatures, from room temperature to just slightly elevated. And then you get filament diameters that go down to around 100 microns for some filaments. That's pretty rare. Usually around 200 to 300 microns above. And then all the way up to 12 millimeters for the cases if you want to build a house. So, some parts of the house. 12 millimeters, half an inch, right? It's a pretty wide filament methods. Build sizes up to several meters, if possible build speeds ranging from 5 millimeters per second all the way up to a meter per second. And you can, one interesting aspect of this is you can do multiple materials. That's one of the reasons why these types of processes are so powerful, is you can have multiple colors, you can have multiple materials with different material properties. The Mark Forge system will actually concentrically put carbon fiber through the center of this. You can, I don't have an image of that, if I should come up with an image of that, but basically here would be polymer on the outside, carbon fiber on the inside. This is looking at the cross section through one of these spoons. So you can get really interesting material properties if you have carbon fiber integrated into these type of constructs. Room temperature methods are, if you look at these, this is being primarily driven by the industries that are biotechnology, where these are seem to be important. I think if I say multiple materials, yes, and then I think the interesting caveat, if I were to edit this table, to actually say you can do biomaterials as well as a caveat. And not only biomaterials, but cells. These are, by cells I mean human or animal cells. But same basic specs. Key players, Stratasys was the inventor of this technology, so they're big. They started with this technology and then they bought out a bunch of other companies as well. So now they have Stratasys now has a pretty wide portfolio of AM tools, but they started out with melt process material extrusion. That's how they started. And I have on here too many to list, right? I can't possibly keep this up. It's like every day there's like this new process that costs even less money now, like $300 you can buy something tomorrow, right? So there's just way too many for me to possibly list. The room temperature processes, this is not too many to list. Vision Tech, this is one of the ones that you saw in homework 1, but Organovo, EFD, these are some companies that do room temperature processes. Okay. So facilities, we have everything from desktop type systems. This would fit the corner of our desk right here, really small. To the Stratasys system, this would occupy about the same amount of space as myself and this podium occupy here. And then this one needs stairs to get in, right? This one's gigantic. So it is a really wide range in terms of the structures and the sizes of the tools that we're talking about. Here's an example of stop the video again. Let's start it over, see if it's better. This is, of course, sped up considerably, but you can see the size of the robotic systems that are driving these and the size of the material structures. This is all, you can see there's like a glass top, it almost looks like a greenhouse. Not a greenhouse, but this is designed to keep the temperature in this fairly warm. You don't get incredible amounts of thermal stresses building in this part. So you don't want to have a really large shock in terms of temperature and the melt area versus what the ambient is. But just incredibly large structures that are being made with these types of processes. We'll see where this goes. There's been a lot of press about these really large structures. I don't know if I'll live in a house that's built by a manufacturing system someday or not. Or my children will. I don't know if there's a market for that or not, but some people do. So I think where it could have a market is building jigs and other things that are supporting heavier industry. Being able to build a very large jig for sheet metal forming or chip building or whatever you want to do that's really large. You want to build this in a fairly inexpensive manner, and you want to do it quickly. It has some serious advantages to it. Again, I don't know if we'll be building houses with this. The military is looking at this to build temporary housing in kind of remote areas. So I think there's some options there. This is a smaller scale version, so we're going to look at what's more typically done. Is an older Stratasys system. So I showed this video on the first module as well, just to show you again. Basic idea is heated nozzle area. It's tough to see the nozzle. It's not moving fast. But that was the best way you can see the nozzle, but this is then sped up considerably. You can make pretty large structures in pretty short periods of time, pretty complex structures as well. You can have support materials, so a lot of support materials that are designed to be broken away or they're water soluble. You can have support materials in terms of the multi-material aspects of this. Okay, materials. I'm not going to talk too much about the polymeric materials because I think people are mostly familiar with that. I'll talk a little bit about the materials that are available for the room temperature processes. I think that's something that this audience maybe not be so familiar, you may find it interesting. But the polymeric materials that are the filament feedstock are basically just polymers in wire form. So this is an example. If you go to Stratasys website, they'll show you everything you can buy from them. And then there's a bunch of other, not OEM type suppliers of all these filaments that you can buy that's pretty inexpensive. It goes from ABSs to a bunch of other nylon materials, all these other things. There's a pretty wide range. I would say any polymer that can be melted, but a lot of the polymers that can be melted, you can use these things. If we get into the fluid mechanics portion, I'll talk a little bit about what the biology of these. Great. Probably going to erase all of my annotations. Yeah, it's all gone. Okay. Well, I'm not writing like truly notes on this one, so so we get to the fluid mechanics portion. I'll talk a little bit more about what I mean by colloidal fluid feedstocks, a bit better. But the basic idea is that we have a pretty much diverse set of materials that can be used for biomaterials. And let's briefly go over this now, but there's a set of biomaterials that are used for synthetic tissues. So if you want to be able to replace a certain portion of the body with synthetic tissues, this additive manufacturing has been a solution for that. So the ability that, say, for instance, you have a very large defect in the body, instead of having to harvest tissue from another place in your body and implant it there, you want to be able to artificially make these materials. This is all doable. So people have found different ways to modify either artificial materials or natural tissues to get them to work with additive manufacturing. So this is an example of a polymer that's artificial that people have made for tissue engineered materials, polycaprolactone. And this is similar idea. This is actually not room temperature. This is heated, where they heat it and then they extrude it through this structure, and they get really small filaments. This material, this kind of mesh type form. Here, this is. I didn't show this as a major type of material extrusion process because this is not major, not many people use this, but this is the opposite of the case of melt process. This is freeze process materials. So instead of extruding this, and then the material goes to room temperature, you actually freeze it as it's going out of the nozzle. And here they're actually printing with collagen. So they actually take, kind of crude, but they go to slaughterhouses and make collagen from these materials, and you can actually print with collagen materials to make synthetic collagen structures. The reason why they freeze it is because the water that freezes and creates all these little icicles, and then it creates voids in the structure. Really high surface area advantageous. So that the freezing process is actually influences the material properties of what you're manufacturing. Not too common, but I thought it'd be interesting to show that. Other things people have done is trying to replicate vasculature, so they can print. This is maybe tough to see, but this is just a little pneumatic printing schematic. This looks like a lot like the EnvisionTEC type systems. They're creating these artificial vasculature systems here. You can see different materials. This is agar, which is a hydrogel material, which is, again, a naturally derived material that they can print with. And so then they're creating these conduits that mimic blood vessels. These regions, so this, again, naturally derived. This one is kind of interesting. This is actually printing with sugar. So you can, the material scientists get really good at modifying material properties. They're able to create essentially a material that's very, very dense sugar and then have the rheology correctly so you can create filaments of sugar. And what this does is that it creates a template which they can then backfill the structure with basically a natural tissue, and then they can dissolve sugar because water can dissolve. Like you apply some water, dissolve, and make jello. Right? So they create this vasculature structure. So there's a lot of interesting ways in which people have been able to modify this. This is my work back in my PhD, where we're looking at how do you make synthetic bone scaffolds. This is how do you create a artificial material that could be then implanted in the body. This is the case of a cranial in the orbital socket region. So what we were doing is this is a ceramic material. So ceramic materials are very, very difficult to process because it takes, in terms of if you were to try and melt process them, it'd be almost impossible. It takes a really, really high temperature to make a ceramic melt. Really beyond what a lot of our tools are capable of handling. So what you can do is you can turn ceramic powder in, modify the rheology or the viscoelastic properties of it, such as it does that transition from solid-like to liquid-like to solid-like again, based on how much the shear stress is applied to it, and get the flow through the nozzle and set. So you can make these structures. This is a multi-material structure, which is a bioceramic. It's called hydroxyapatite, but that's not too important. But you can make these three-dimensional structures that look a lot like what you see coming out of a MakerBot. And so this is an example. We had different densities of these structures in different regions. We can have really, really highly dense. This is the low density. This is the really low density area and really high density area. This is a CT scan of what's on the inside, but we have these different regions in different parts. So what comes out of this system here is not the final part. It's basically all this powder, and it's very tightly compacted. Essentially, the van der Waals force of the powder all come together, and then you put it in a furnace at the very end, you fire it, and it becomes fully dense. Okay. Other examples. This is I said you can print with cells. This is work out of MIT, where this is really, really simple. This is just a low pneumatic pump. This is the Organovo system, and you can use basically gelatin or gelatin hydrogel, and you can embed cells in it as well. So because it's all at room temperature or just slightly above room temperature, you can keep cells alive at 37 degrees C. You can have cells embedded in the structure. And so what you're doing when you're making this artificial construct, you're priming the system to already have cells in the system, in the structure you're depositing. So then this image here is just showing this is the void space, this is the filaments here, and then what's lighting up with the fluorescence microscope is essentially cells that are Okay, and then the last thing I wanted to show before we adjourn today, start getting into more of the heat transfer part, the heat transfer module, is kind of hybrid systems that are coming into being. And I think it'll be even more important in the future. So a lot of these materials, like this material, if you were to touch this material, it'd be incredibly soft. It's not actually all that viable as a material because it'd be really tough for a surgeon to ever handle. And so people are looking at how do we use the ability to create structures with multiple materials with material extrusion to make structures that are both mechanically rigid and have, say, cells in them. So if you look at what's going on here, this is just a schematic of a material extrusion system where they have TCL, which is a fairly compliant but much more rigid than the hydrogel polymer, like caprolactone, very common biomaterial. So this looks like a MakerBot here, exactly like a MakerBot. It's a heating element, melts it, extrudes, and then it solidifies when the heat is taken away, right? And then right next to it, they have 3 room temperature material extrusion systems. And so these are actually not room temperature. This would be at 37°C. These are trying to keep cells alive. But the heat is primarily resident in the hot material and doesn't really transfer to this hydrogel material right next to it. So you can make these constructs that have rigid structures in them and also very, very soft structures, cells embedded in them. So you can have these structures where you have PCL for rigidity here. You have then these hydrogel materials that are not very rigid at all, but you can have cells in them. You can have cell type A, cell type B, so you're priming the system. You can also have these channels in them to create artificial vasculature. So these are all very much emerging processes that are coming into being that I think will be even more impactful in the future. So you can make structures like this. And here showing the cell activity. This was cell type A here and cell type B here after everything was printed. So a lot of things that you can do. Sorry if you are queasy with bloody pictures. You may want to divert your eyes right now. It's an issue for anyone. But these have been implanted into animals, showing the ability to basically fix defects, etc. Here's the examples more examples of that, showing that these constructs that people are trying to build are all additive manufacturing technologies that are being used. Any questions of that very quick overview of some of the materials that are being used? Okay. This next we're going to get into heat transfer models, which is a pretty sharp deviation from this. I think I'll just wait until Thursday to do that. That's all right with everyone. Yeah. All right. Just a reminder for those of you who walked in late, office hours are today from 3 to 5, and they're tomorrow from 4 to 5. Because homework's due on Friday, right? Okay. Yes. Oh, that's another thing I wanted to ask. So if you go to the comment and just click on module 5, the preview for some reason doesn't show. You download it, I don't know why Carmen doesn't do that. I don't know.